I'm sorry about the noise that is in the background, but today we are going to talk about multiple linear regression. And it's going to be a brief lecture. And after we talk about multiple linear regression, we're going to set up a model. We will then illustrate how to do both simple linear regression and multiple linear regression using SPSS. Now, to discuss multiple linear regression, I'm going to share a PowerPoint slide. I might illustrate on the whiteboard for the benefit of those who are in the class. The simple question is, last time we talked about simple linear regression, and I'm going to put up, I'm going to share my PowerPoint slide. All right. Are you seeing my PowerPoint slide? Hello? Yeah, I'm talking to those who are online. Are you able to see my PowerPoint slides?
Yes, we can see it.
All right. Thank you very much. All right. Now, last time I was on Zoom from a distance, we talked about simple linear regression. We talked about linear regression in general, and then we used simple linear regression to illustrate. Now, a regression model is a model that shows the relationship between two variables. One is called a dependent variable. Please stop that. And the other is called an independent variable. Let me stop this share of multiple regression and just go back and briefly review simple linear regression the way we talked about it. So I'm going to go through a quick review of simple linear regression, and then we will get back to our topic for today. All right, so this is simple linear regression that we talked about on April 24. I was at a distance, and we discussed this in class. Okay, we discussed this in class. So let's go through it very quickly. All right, so this was what we had for simple linear regression. All right, like we said, simple in regression analysis, we are talking about the relationship between two variables, okay? We'll call the two variables y and x. And y is the dependent variable, and x is the independent variable. For example, how much does a family spend on food? That is a dependent variable. The amount of money that the family spends on food could depend on the number of persons in the family. So the number of persons in the family is the independent variable. And our objective is to ask the simple question, what is the nature of the relationship? Okay, what is the nature of the relationship? And as we said, we want to know first of all the nature of the relationship, then the size of the relationship, then how strong is the relationship. Please stop all conversations, all private conversations. And the relationship could be positive or negative. This is a positive relationship, y as a function of x. And for example, y is equal to 10 plus 5x. Essentially, in a regression model, we are looking at what you all know as the equation of a line. Okay. So now, we're essentially looking at what you call the equation of a line. Okay? The equation of a line. So, this equation, you know that A is a constant variable, which means when x is 0, then if x is going to be 0, and A is the value of 1. So the values of y depend on the values of x. Okay. The relationship will be positive. We have an amount and y equal to 10 or 5 and x. So now this is a positive value. Doesn't have to be always positive, but this is a constant. Constant value is 10. Now, the nature of the relationship between y and x will be positive, which is we have the equation of the line that goes here, the constant is 10. Okay? And this is y equal to 10 plus 5x. So every time that x increases by 1, then y will increase by 5, as you have in the illustration. Okay? Now, the relationship will be negative. For example, y equal to 5 minus 2x. So in this case, we will have the constant is 25, and as x increases, y will increase. So in this equation, each time that x increases by 1, y will increase by 2. Okay? Does not always have to be whole number, to be a decimal. Okay? And to do a little bit more of analysis, sometimes we have to linearize a non-linear function by using logs and other mathematical relations. So that's to create a linear relationship. Okay, so the family has a function. If you have a power function, linearize the power function is linearize using the laws of the values. Sometimes functions instead of solutions and whatever relations. But here we're going to look at simple models. So now, when you look at the model that we have here, why is it not showing everything? Okay. Whoa. Excuse me. Yes, this is. All right. So now when you look at this function, y is equal to 10 plus 5x, what you observe is that the line fits perfectly into the points, right? And if you also look at the other function, y is equal to 25 minus 2x, what you also observe is that the line fits perfectly into the point. And so the question then is, if you already know how to plot a graph of y is equal to equal here, what does regression analysis do different? That was the question that we raised, and we answered that question. Remember, I'm just going to go through the lecture very quickly because I did that online. And you all get the email about the YouTube posting. Okay. So you already have looked at the YouTube lecture. And so this is just a quick rundown. So if you already know how to take an equation, y is equal to 25, y is equal to a plus bx, and you can create values of x and then determine values of y, what is it that regression analysis adds? Okay. Now, when we do regression analysis, essentially we are looking at a relationship that is not exactly found. Okay? And that is the big difference, which is what we illustrated the last time. Okay. We have here the relationship between y and x. Here, the number of copiers sold as a function of the number of calls that the salesman makes. All right. Like I said, what is it that regression analysis asks? You can see that from the extreme right chart, you can see that the number of calls that a salesperson makes does affect the number of copies sold. But the relationship is not exactly perfect, right? There are other factors that would affect the number of copiers sold based on the number of calls made. Okay, those factors could be the need of what is called. They may not be the copier. The other is their ability to pay for the copier. They may not be able to afford it. The other could be the personality of the salesperson, the way they talk, the way they're able to convince you, convince the customer to buy a copier. And maybe this is not the copier that the customer wants. Those are all facts. So the relationship between number of calls made and the number of copiers sold is not exactly perfect. And so what we do then in regression analysis is to try to fit a line perfectly in the middle of the what we call a scatter bag. Okay. So you can see that the points are scattered. So we try to estimate the line right in the middle of the scatter bag. Okay. And so our objective then is to estimate A using an estimate of A. More. Y is equal to A of dx of E. In the sense that we recognize that an expression is relative between Y and X. So our ability to predict Y using X is going to have error in it. And so we estimate A using A hat, which we say that A hat is an estimate of A. But exactly what it is. We estimate B using B hat, which is to say that B hat is only an estimate of B. Okay? So, once we estimate A and B, the next thing then is actually ask ourselves, okay, how from is the relation? How one is a relationship between X and Y? And essentially, what that says is what percentage, to what extent the change in X actually bring about that change in Y. That's right. Okay. So I was analyzing it by saying what percentage of changes in Y by changes in X. What percentage? We do that using what we call the coefficient of determination. I'll put it out for the coefficient of determination. So that says, for example, that 85% of changes in Y are explained by changes X. So what explains the percent? No, random errors, like we said, changes in the number of copies sold really affected by the number of homes made. But then these are the factors that anti needs of the customer, affordability of the customer, who will then explain why we cannot predict exactly progress. And then lastly, we need a case of hypothesis. Okay? The hypothesis as yourself. The changes in S significantly affect this part. And I'll give you an example. Give me an example. When we plan to do this, think about the intersection of Woodland Street and Flagler. Okay? And we ask ourselves every hour how many vehicles pass through That is every hour for the next 50 hours, 60 hours, 80 hours. And it's how many variables pass in each during each hour, how many variables pass to the section. So you take note of that. That is the independent. Then, after that, how many babies were born at the hospital? Yeah. That is your independent. If you do a regression model on that, you're going to get the but you're not going to make this model calculate. Will depend on the number of variables that pass section. No. There's more models. It might actually be that if you took that on the section, you had possible. That's not a question. But if you take that on the section, or even maybe on instant calculation and therefore, you will not find the significant relation. So this is why we must happen. It might be that the independent variable does not actually affect even that. So we did a list of policies and go into so we have different hypotheses. Different hypotheses of the slope. And why should work with it? So we take the hypothesis, the hypothesis will then be that B is equal to 0, which means that X does not significantly affect Y. That is X does not significantly and alternate hypothesis is that B is not equal to 0, which means that X significantly affects. That's ways to get a hypothesis. Once we figure out a hypothesis, we select alpha, the level of significance. Alpha, and that gives us the critical Z value. That gives us the critical Z value. And then we calculate equal to the plus or not hypothesis. So calculate C, which is we have a non-hypothesis, divided by the B active. And so the decision rule, as usual, that if C is greater than or equal to C star, we reject the non-hypothesis that is equal to 0. Now, the non-hypothesis does not always have to be 0. The non-hypothesis does not always have to be 0. Why? Because there are some issues that you will test when the non-hypothesis is 0. A good example will be the price elasticity of demand. You don't have a demand. You have a price elasticity of demand. You have not had a price you don't have a demand. Okay, you're an engineer. All right. All right. Now, so you see, here we have the theory of the land, right? Quantity demanded price. Right? There is an inverse relationship between price and demand. But even in linear function, the percentage change in quantity demanded, or by percentage change in price, is called the elasticity of demand. Right? That is the responsiveness of quantity demanded to the price. Now, for example, if the 10% change in price leads to a 5% change in quantity demanded, then the elasticity is greater than 10 times 2. So the elasticity of demand is greater than 1. So we say that this group is price elastic. Okay? The percentage change in quantity demanded is 5%, percentage change in price, but the percentage change in quantity demanded is less than 1. Then we say this group is price elastic because there is a less than equal proportional exchange in quantity demanded in price. So now in that case, if you want to test the price elasticity of the group, then our hypothesis will be less than 1 or greater than 1, depending on whether we hypothesize that this group is price elastic or this group is price inelastic. Okay? In engineering, you probably also have issues of elasticity. Right? That is the responsiveness of say, an elastic band in the market. So, that example. And so, if not about this, does not always happen. First of all, if you not have this, for example, test for hypothesis where the independent variable significantly affects dependent variable, that is 1. So your first test of hypothesis is that B is not 0. But then you do the next step and say, what would be the size of B? B be 1, B be less than 1, B be more than 1. Or even if it's more than 1, is it between 1 and 1.5, or is it between 1 and 1.9? Get the idea. Right? So you're going through 2 stages of hypothesis test. And we do that quite often when we do the analysis. Based on hypothesis, okay, we reject this hypothesis. How about the next? All right. So having done that, I'm going to go through the slides for the benefit of those who are online. Then we move into multiple regression so that we refresh what we had last week. As we said, we estimate A using A hat, and that is the formula, and which brings me to your project. Okay. Brings me to your project. You can use Excel to do your calculations and your estimations, or you can use SPSS. Some of the data sets are SPSS, some of the data sets are in Excel. Some are in both SPSS and Excel. But if you choose a data set that is in Excel and you want to do SPSS, please send me a note and we're going to translate the data set. It's easy to use SPSS to put in Excel data sets and compare them with SPSS. That's all for you. But I want to see your work. So, I want to see your work. A student has already submitted project. Use MS Excel to do a regression model, and then There's also a link. You must submit your project online. Not gonna take 2 minutes. Right? I mean, makes me laugh. I created a link and I'll show you the link. All right. So, this is the formula for the simple linear regression. Okay. And so we estimate B hat. Yeah, this is the regression model on sales and sales calls. As you can see, we estimate B hat to be 0.26, which actually means that to sell one copier, the salesperson has to make approximately 4 calls. Because for each time that X, which is the number of calls, goes up by 1, the salesperson sells 0.26 of a laptop. So you need to make approximately 4 calls to be able to sell 1 laptop. Get the idea? I mean, 1 copy. All right. So this is what the estimate gives you. Now, we also then, once we do the estimation, we use our estimation to create what we call a model. So this is the model. The model is Y is equal to 19.98 plus 0.26 times X. Now, what does it mean? Now you say, the salesperson makes no call. Why is it then that they are able to sell 19 copies? Well, here, there's an implication here for the kind of we're looking here at managerial situations. Let us say that we are looking at an arrangement where the salespersons are there, right? Walk into the showroom, and you talk to the salesperson. Am I correct? They don't have to call you. Walk into a showroom where they're selling copies. The salesperson will now walk you around and show you the copiers and display the copiers to you and say, this is good, this can do this for you, or that can do that for you. And they're able to sell the copy without having any call. Right? Now, the second salesperson will become the call and call companies. Call them and say, we sell copies. And we'll then from somebody who makes a decision about what to think of as a company. Am I correct? So by doing that, they are able to sell more. Very idea. So this is why you get this kind of model where Y is equal to what is the model here? Okay. And so A hat is 19.98. And so the slope is 0.26, which we already said. So this is the model equation, 19.98 plus 0.26x plus E. So if sales costs increase by 1, the salesperson will increase sales by 0.26. So about 4 sales calls will bag 1 additional sale. You get the point? Okay. So if the salesperson just sits in the office and customers walk into the showroom and talk to salespersons, this person who makes no call is likely to sell 19 copies a month or a year or a week. Okay? We are not told what the time frame is. All right. So now we ask ourselves, how strong is the relationship? That is the formula which we explained last week. Okay, that is the formula. R squared is equal to B hat times. See the expression there, we went through it last week in class, and we showed how to use Excel to do that calculation. Okay, and so The coefficient of determination here is 74.6%, which is to say that nearly 75% of sales is explained by the number of sales calls. Okay, that's what this result tells us. And then the remaining 25% is explained by all the other factors that we talked about. Okay. Now, we went through a test of hypothesis, and we also showed how to calculate the standard error of B. Okay. We went through that. We calculated Z. This is the spreadsheet. Okay. And then we provided some other examples where, for example, this is the dividend model. This is the dividend model. What is this model about? There's a theory in finance that companies that pay dividends also increase the price per share of the stock. Okay? And what is behind that is, think about it this way. Companies do not always pay dividends. You buy one share of stock, you expect a dividend at the end of the year if the company makes a profit. But what the company can make a profit and decide they will not distribute dividend. Do that. Now, suppose you're a shareholder. What do you do if you want money? What do? No dividends by bottom line. But you have shares. And the company made a lot of profit. What do? Right, a lot. Shares. Sell shares. You take some of the shares and sell it. That's right. Okay. And get paid. All right. Now, the whole argument is that a bird and what quote. The alternative is you don't sell it, but the value of the share goes up anyway because of the profit the company made. And you're saying to yourself, okay, I bought this share for $50 as a 10% for profit rate, and so now my share is worth $1. Okay. So instead of getting the $5 dividend, you expect that the company will reinvest the money, and next year your $50,000 will now be worth $60. So the wealth grows. But who says that the company will not lose money? So shareholders will sell their shares, some of their shares, in order to get what the dividend this year. Okay? So this is the whole idea. But there's a theory that in finance that shareholders do not always rely on increasing value of the share. And so those companies that actually give out the dividend, their share prices will go high. So we have a dividend model, which says the price of a share depends on the percentage of dividend that the directors pay. Okay. So we have a regression model for that. There's a whole lot of research on it in finance. Okay. This is a model of the maintenance cost of a vehicle depending on age, okay, depending on mileage. That's another example, cost of maintenance, the dependent variable, and age in years of the bus, the independent variable. We have a model for that. Okay. That is the data for it. Those are the calculations that we made. Okay. All right. And of course, we went through a test of hypothesis. Now, Okay. So now we can see we went through the MS Excel model, right? Process. And we got some results. But we can use SPSS, or I can use Excel, but I prefer SPSS, to actually do a regression model. Okay? You do a regression model. And so this is the kind of printout you get. See B is the slope, the intercept is there. So the constant is 3.379 here, and the size of the family is 0.414. So for each additional person that is in the family, you spend for the 1 month like that, or for $1 more in food. We are not told exactly how this is measured. Okay, and 76.7% of expenditure on food is explained by the number of people in the family. Okay. All right. So now, I'm going to now pull up the multiple regression. All right. Wait a minute. Something is echoing somewhere. Okay. So now we were talking about the relationship between a dependent variable and one independent variable. So now go to the next stage. Now go to the next stage where we are looking at multiple linear regression. Now, y, the value of y, dependent variable, depend on two or more independent variables. And so, specify a model of y equal to a plus b1 x1 plus b2 x2 plus b3 x. Plus error. Now, we cannot easily use the simple expression set of spreadsheets to do this. But to put it very simply, you can assume that you have the y and by y vector and x going to the double line and there as and by k matrix. Then you can use the Gauss method to actually estimate. What you have here is y equal to x. Yeah, and this is y, and so b, which is actually k by 1, equal to y equals x. And So from here, you're going to get a DA525 vector. So that way, you use methods to actually estimate the vector of the values. But we're not going to go through that here. If the ever of a class M then we'll go through that method. Again, you may have not done this already different. If you're not going to study it from this theoretically, then those to estimate the Y, so that the theoretical constructs of what it's for not putting a repair. But if God at the end of the year, you think that Y, well, you define but B1 X1 plus B2 X2 plus B3 X3 plus B3 X3 plus E. That is what we're looking at here. I'm going to go through the outline slides. Then we'll do some estimation using SPSS and see how we then interpret the model. And here we're going to use an illustration that wages depend on years of education, gender, tenure on the job. So that will be the model. But you can see here very simply that Y is a function of two or more independent variables. Okay. All right. So as you can see from this model, we have two or more independent variables to estimate the cost of providing heat in a home, which depends on the mean temperature outside during the periods here, whether there is insulation in the attic or not, the number of inches of insulation in the attic, and the age of the furnace. These are three variables that could affect how much it costs to provide heat in the house. These are results. These are SPSS results. And so, as you can see from this result, the R square, which is the strength of relationship, 80% of the cost of heating in a house is explained jointly by all those three variables, 80%. There are 20 observations here. So now, let me see if I can make this a little bigger so that we can look at the real things there. Are you seeing it bigger? Let's see. Well, it's not getting any bigger, so. I'm sorry, can I make it bigger? But you can see here, see where it says the coefficients. Can you read the coefficients there? Okay. Now, it shows that the intercept, the basic cost of heating a house will be about $427. Okay. During the year, I believe this is during the year because they're looking at mean temperature. And if the insulation, depending on the thickness of the insulation, the thicker the insulation, the lower the cost. So it has a negative value. And the older the house, the higher the cost. Okay? So it has a positive value. Now, the question then, when you test the hypothesis, Remember, I always say use the absolute value, or you can read the p-value. Okay. Now, if the p-value is less than your level of significance, then you reject the null hypothesis of no significance. Okay. And so you can see here that temperature significantly affects the cost of heating a house, and also the insulation. The level of insulation, thick the insulation is also significantly affects how much you spend to heat a house. While the age of the house may, as you see it there, the p-value you can see is 0.148, which is much higher than the level of significance that you choose. You can theorize about this. If I had the data, I would go back and look at houses back in the 19th century. You know why? Because then they probably did not have resources for insulation. And so older houses might be more expensive to heat if you put that data from that time. But in our modern age, in our present day, we have resources for insulation. And so the age of the house may not actually affect how much you spend. Because if you have an older house, first of all, you might fix it up. But even if you don't, you put thicker insulation, which will help to reduce the cost of heating. You get the idea? And so this is why we have before. So when you do regression analysis, think about, first of all, theorize the result that you're going to get. Once you theorize, then you can actually test your theory. And this is what regression analysis is about. This is what we do in statistics, is to take data to test the theory of the process. Okay? So now that is the model, the model equation. And so having done that, okay, okay, and I'm going to post this. Today's lecture, I'm going to post it. Okay. So now, once I'm done with this, I'm going to now pull up the SPSS, so we can go through the process of doing regression analysis, multiple regression using SPSS. Okay. This is a model of the price of a house as a function of size, distance from the city, and the number of bedrooms. As you can see here, the basic price of a house, just if you have it, like essentially, you ask yourself, what does this mean? Now, a house is usually built on a piece of land. So if you have 0 bedrooms and what have you, essentially you're talking about the price of the land. And so this is what the constant here, this constant would represent, essentially the cost of land. And again, depending on where you are, I've seen different models of houses and prices. If you are in a big city like in New York City, this constant will be running like 150,000, 160,000. But if I'm looking at houses in rural areas, that constant would be like 50,000. That's what I have, observed from my own studies. Okay. If a house is further away from the city, as you can see, the price is reduced, as opposed to when the house is closer to the city. And if the house has many bedrooms, depending on how people value bedrooms, the price of a house goes up at about 10,000, okay, for each additional bedroom. And you can see the p-values are all way below the level of significance. Okay. Okay, you can read through this. That's about dummy variables. We didn't get to that level of studying multiple regression or something called a dummy variable. The dummy variable are variables that are binary, like male and female. Like the house has a pool, a swimming pool, and the house does not have a swimming pool. The house has a garage, or the house does not have it. Okay, those are called dummy variables, and they take a value of 0 or 1. All right. For example, here, this is a model of wages. No, this is not. Yeah, annual wages in dollars. Okay. So what if somebody has no education, no experience? Of course, there's no such thing as not having a gender. And, we're not talking about a union. What is their wage? You can see that somebody like that will probably not have is not employable. Okay. And you can see here that the value of the constant is not significant, which means essentially it's theoretically 0. You see the p-value. You can see the p-value is 0.107, which shows that you are not able to reject the null hypothesis of 0 for when these variables are all 0. Okay, the constant becomes 0. So essentially, somebody who has no education and no experience is probably not employable, and so will not have anything. So in advanced modeling, we can choose to take that out. But you can see the higher, the more years of education somebody has, the more income they make. And the more years of experience, also the more income they make. And here, gender, 1 for female and 0 for male, shows that the discrimination against women, one way or another, or for some other reason, females make less money, okay, than males. It could be due to discrimination. It could also be due to where they are working. For example, suppose you come in a workplace and the females are all admin staff, custodians, and what have you, and the males are more in the managerial ranks and what have you. So depending on the way they are deployed, females will have a lower average wage. Okay, and this is what this model was supposed to look at. And here you can see also that union, belonging to a union, is negative, but it's not significant, which means that there is no discrimination against those who belong to a union. Get the idea? Okay. All right. Now here we are talking about other issues that we're not discussing here because we are not taking this modeling beyond just simple model. There is something called multi-pole linearity in regression analysis, multiple regression analysis. There's something called multi-pole linearity. Now, essentially, what it means is there are 2 variables there, those who are that are parallel. Okay? They're parallel in the sense that if you take 2 parallel lines, there is no intersection. So you cannot actually estimate how one happens. Yeah? Now, here's an example of parallel lines in analysis. We look at the cost of maintenance of a bus and how many years after the bus takes. Suppose you also have data on the mileage of the bus. Then you realize that if you put those 2 variables in a regression model, they are parallel variables. Because the older a bus, the more mileage you know. Am I correct? So the two variables, mileage and age, are going to have a strong correlation with each other. And therefore, you may not be able to separate their different effects on cost of maintenance, unless you find a composite variable. For example, suppose a bus is driven, one bus is driven more than the other. So in as much as there is a age, you drive this 10,000 miles a year and you drive this 2,000 miles a year. And so you can actually take a variable like mileage over age, which now gives you a different variable, a positive variable of how intensely you use each bus. And so you take those two variables out and rather estimate for intensity of use as an independent variable. You get the point? Okay. So let's, but we didn't get to that point. We'll talk about multi-linearity. So let's do an SPSS. Okay. This is a multiple linearity solution. I was very much interested in this multi-linearity as a student, and I did a couple of papers on them. I'm going to stop share. Okay. Before I leave, I'm going to take down the names of those who are online. Everybody put their name down. Good. I'm going to write down. So please just allow me a few minutes. Jerry Luke. Luke. Sorry. All right. I'm going to put up a model here. Okay. I'm going to share. All right. Can everybody see my SPSS file? Okay, and then those online, can you see my SPSS file? Speak up.
Yes, we can.
All right, thank you. Now, this is a model of houses and their prices, okay? The model of houses and their prices. And so I'm going to do a multiple regression model of the price of a house as a function of the size of the house and also the age of the house. But as you can see here, there is there's no data for the age, all right? So I'm going to create the data for the age. The data for the age will be the date sold minus the year the house was built And so I'm going to transform. I'll compute a variable, and I call that variable age. Okay. Call that variable age, and age is equal to the years sold minus year built. See that? Very simple. So I go through a transformation and I say, okay. And so I have age. Get it? Okay. Now I can also think about including the lot square foot, that is the size of the lot on which the house is built. Some people like big yard, all right? And they're willing to pay for it. Okay? I grew up a lot around big yard. So when I was trying to buy my house in New York, I kept looking for a house in big yard. And that made it a little costly. But some people don't care about the size of it. Get the idea? Some people don't care. They just, in fact, they don't care for a number of reasons. What am I going to do with it? For one. Number two, that means you have a wider area to play. All right? And so if you don't like to sweep yard, or if you're a guy and you don't like to do the lawn mowing, so you don't want a yard because you don't want to mow that much lawn. Is that correct? Okay. So, but still, we want to know if the size of the lot affects the price of the house. It might also be that the size of the lot, when people have a bigger lot, they want to build bigger house. So that can create a problem of multi-collinearity, because you will not be able to separate the effect of the lot size from the size of the living space in the house. Okay. All right. So, max. So you go analyze. Always, when you want to analyze, you must begin from analyze, regression. Okay. I'm going to just use a simple linear model. The dependent variable is the price of the house. The independent variables are age and the size of the living space, how big the house is, and let us include lot size, hoping it does not create a multi-collinearity problem, because if there's a multi-collinearity problem, you might sometimes not be able, you get a zero value automatically. Sometimes, okay? Or you get coefficients that are not testable. But we're not at that level. So I'm going to say, okay. There you go. Okay. So these are the coefficients. As you can see here, the age is significant. Older houses sell for more. The living space is significant. Lot size is not exactly that significance unless you use a 0.05 level of significance. Okay, but you can see now, why is it? And it is telling me here that these variables are all zero. Of course, if there's no, house as built, then you probably won't be able to set the line. In any event, you can see the coefficients, and you can test the hypothesis, each of them separately. Okay, you have to test each hypothesis separately. And this is simply how to do regression analysis, multiple regression using SPSS. Okay, you can do it for simple regression, you just put in one variable. So what? Excel has a regression model, but I don't use it. Yeah, I did say that. If you prefer to use Excel. Okay? If you have data set that you prefer to use SPSS, send it back to me. I'll convert it to SPSS and send it back. You can use any software you want. You can use Minitab. Right? You write Minitab. That's what you have. Any software that you have, as long as your results are fair and you must write out the model. I don't want to see just that. I want to see that, and I want you to write immediately. Okay. Okay. So the other thing I set out instructions is two people cannot do the same test. Right? For example, we just had this on housing on the side. Okay. Somebody can use, people can use the same set. But you have to test different hypotheses. For example, you can test the difference in price of certain income. You can do a regression model. But if somebody says they're going to do a regression model using this data, if you come with the simple, I'm going to say you can do a hypothesis test for two populations and there are variables there, but you cannot do a regression model testing, even if you wanted to do a simple regression. Yeah. I also set up a link to submit the assignment. So do not send me your paper or an email. Okay? It's just going to make life. They have the package there. Set up a link. Okay. Having said that, yes, you have to email them what you want. No. Then you have the deadline of the project. So the project send me your model as soon as possible. Today is MAY1. So by the weekend, send me something. It's not going to take a lot of time, but you must say why you have to. But put it this way: why is it that what we're doing is interesting? Why is it interesting? So I have to describe test why you want to test it, why is it that interesting thing to test. Right? So that's where we start. Next week we're gonna have this. A lot of students have asked, one or two some review. So next week I'm just going to come up and solve some problems. Any problem that you think you should please send it to me. So the data set selected with emails. Yeah, all right. Any other questions? All right. When you do your SPSS, pattern and paste this, everything on MS1 and right off what it is that you see. I want to test the hypothesis on, say, the difference between alveolar lot size in broken things. Okay, say that explain to me why. So run the report in MS Word. So all your results from Excel or what have you, cut and paste them into MS Word. But I want to see also your SPSS. Fine. All right. Okay.